Dirac equation, where G is a gyromagnetic moment factor, gyromagnetic factor here. Q is the charge of the particle, m is the mass of the particle, and s is its spin, and mu is the dipole moment. So in other words, this equation 1 is saying that the spin and the dipole moment are related. In other words, so as you see, they are vectors. In other words, so if I can somehow know the spin of the particle, in which direction the spin is pointing to, I know in which direction the dipole moment is pointing to. As if I know the particle involved, in other words, if I know the charge and the mass, if I know the spin, I know the dipole moment. Okay? Right? So if I know G, but if I'm trying to measure is the value of G, so I'm trying to test whether this G is precisely the value predicted by the Dirac equation. The Dirac equation predicts G to be equal to, okay, that's using classical field theory, not quantum field theory. In classical field theory, G is equal to, what I'm trying to say is, if you take into account just 3-level diagrams, G should be equal to in quantum field theory, okay? And that's it. So if there are higher order effects in quantum field theory, this G should be a bit different from 2, but not much different from 2, just a bit different. So, okay, let's say I'm trying to test whether these G's should be equal to. If this G is different from 2, I say we have an anomalous dipole moment, okay? So if it's equal to, there's no anomaly, so it's just magnetic dipole moment. If it's different from 2, I say it's anomalous magnetic moment. So the way they quantify this G factor is writing like this. They define a mu factor, which is G minus 2. If A is different from 0, then there is anomalous magnetic moment. Okay, that's what you do. And then if A is larger than 0, there is a positive contribution to the magnetic moment. If A is negative, there is a negative contribution to the magnetic moment. So that said, knowing quantum field theory, you know that there are loop corrections to a particle. So a particle, mu, can couple to a photon. This photon is a magnetic field, okay? This is representing a magnetic field. But this mu is traveling. But as it travels, it might radiate off a off shell gamma, which is this guy here. Let me zoom in. It might radiate off a gamma and then meets a muon, the other leg. In other words, so if you see a muon traveling, there is no way you can determine whether this muon radiated off a gamma, because you just see a muon. You don't see if the gamma left the muon and came back to the muon. You just saw the muon. There's no way you can assess whether a gamma was exchanged, or a Z boson, or a W, or whatever. So you just see the muon traveling. So this correction to the propagation of the muon, some of these terms can give rise to a magnetic moment. Okay? It depends on how the things go. So these quantum corrections to the muon magnetic moment give rise to an anomalous magnetic moment, because the number is not 2, it's different from 2. If there is a discrepancy between theory and experiment, I call this an anomaly. So anomalous magnetic moment is one thing. Anomalous is being different from 2, because it is different from 2 because of quantum effects. But there is a discrepancy in the anomalous magnetic moment. It's something else. So if there was no discrepancy, it's just an anomalous magnetic moment. Why? Because the value should be different from 2 because of quantum effects, but if the theory and the experiment agreed, there was just an anomalous magnetic moment, and so prediction from the standard model is correct. Here it is. So these are the lowest order standard model corrections to A mu. Remember, A mu is this term right here. It's G minus 2 over 2. It's just a definition, okay? That should be equivalent. It's just the definition of A mu, the anomalous magnetic moment. So you have QED corrections, like when you exchange a photon. Weak corrections when you do exchange a Z or a W boson. And you have hadronic corrections when you have quarks in the middle. So muon does not couple to quarks easily, so it has to go through something, right? You don't have muon then quarks. So you have a muon here in the left one, and you get a muon, and there goes a photon. The photon, there's a photon, and in this loop, they are all hadrons. And the hadrons mass are not easy to compute, and this diagram is not easy to compute. This is called vacuum polarization. Okay. And this one, the letter, is the hardest one to compute. So it's very hard to compute the standard model prediction for the last diagram. Okay?
Yes.
So at this moment, it's very important to know that the standard model prediction is not solid.
So it would be okay.
It's not solid in the sense it's solid, but it's not precise enough. Okay? So there are, we call it theoretical systematic uncertainties in the standard model calculation. Okay? That they are not easy to assess. And at this point, there are several groups have computed this diagram, and they found different results. So then it's hard to quantify precisely the standard model theoretical prediction for A mu.